I welcome you all to the session of engine system and performance, and today we shall discuss about the measurement of indicated work, and then we shall solve one numerical problem on this particular topic. Until now we have discussed about the measurement of fuel and air flow rate, measurement of engine speed. Also we have discussed about the measurement of needle lift, which is also important to know the amount of fuel to be discharged or drawn into the manifold or engine cylinder. So, indicated work, you know that this particular quantity, that is work done by the gases inside the cylinder, is one of the important quantities to be measured essentially for the estimation of engine performance. So, if we would like to measure or quantify engine performance, indicated work is one of the important quantities. Now, we have studied in our undergraduate internal combustion engine course that work done by the gases on the piston is essentially the indicated work, right. But certainly work which is available at the shaft, output shaft of the engine is not the indicated work, because there are some losses, frictional losses. So, let us discuss today this measurement of this important quantity, and then we shall solve one numerical problem. We all know that as the piston moves between top dead center and inner dead center, so piston location changes inside the engine cylinder, certainly pressure inside the cylinder will also change. If we tell it in other way, that gas pressure inside the engine cylinder changes, which in turn changes the work done or piston movement even. So, work done by the gases inside the engine cylinder can be expressed. So, if I write, so work done by the gases inside the cylinder, within the cylinder, of course of engine is W, and that equal to cyclic integral f dx. Okay. So, you know that F is the force. Okay. Now, this can be written again cyclic integral P dA into dx. Okay. So, this typically that if we try to write it in a more accurate form, it should be area of the piston. So, work done by the gases on the piston face. So, area of the piston. So, this P, that is pressure of the gases within the cylinder, which is continuously changing as the stroke of the piston changes, that is from intake to compression stroke, compression to power stroke, etc., etc. This AP is the piston face area, and dx is the distance traversed or moved by the piston. So, the cyclic integral stands that work done per cycle. Essentially, if we talk about 4-stroke engine, 2-stroke engine, so all these engines, 4-stroke, 2-stroke engines, are operated following two different mechanical cycles that we have discussed, depending on the type of combustion. So, maybe 2-stroke petrol engine, 4-stroke petrol engine is there. So, essentially depending on the type of engine we can have number of strokes, or we can have that engine can be classified based on the types of combustion as well. So, now whether it is a 4 stroke engine or 2 stroke engine, all these engines to execute several processes, all these or all these processes, several processes of these engines are executed by a cycle. So, this work cyclic integral indicates work done per cycle. So, this is work done per cycle. Question is, that as I said you, the pressure of the gases inside the cylinder changes continuously. It is not very easy to measure pressure variation. So, target should be to measure instantaneous variation of pressure in the engine cylinder. There are nowadays sophisticated measuring devices are available with the help of electronics or digital technologies, but still the concept that was introduced to use mean effective pressure. So, that means if we go to the next slide, we can write that W, that is work done. So, that equal to mean effective pressure MEP. So, this is mean effective pressure or average pressure. As the gas inside the cylinder changes continuously, instead of calculating or determining instantaneous pressure, it is convenient to write the work done in terms of mean effective pressure that you have studied in your undergraduate course. So, mean effective pressure into, if we write area of the piston into length. So, essentially this is again should not be dx, because the moment we are trying to write in terms of mean effective pressure, we can write that is the stroke length Ls. So, this is stroke length and this is area of the piston that we have already defined. So, essentially we can write this is Vs, that is stroke volume. Okay. So, question is, this is very convenient means of measuring work done by the gases within the cylinder. We could have calculated instantaneous pressure using state of the art devices, but instead the introduction of the concept of mean effective pressure is also equally good to determine the work done by the engine. Now, if we try to know essentially the pressure, mean effective pressure. So, the pressure inside the engine cylinder is continuously changing, and work done that will be calculated using the pressure variation and its average value inside the engine cylinder, that is typically known as indicated mean effective pressure, and essentially work that we will be calculating is indicated work done. So, if I write indicated work done, so indicated work done per cylinder per cycle. Per cycle, that equal to can be obtained this indicated mean effective pressure, which is multiplied with area of the piston into stroke length, that is Vs. Okay. So, question is, as determination of work done or indicated work done is very important to predict the performance of the engine, next we shall discuss one method to calculate or to have some information or to have some quantification of indicated mean effective pressure as the piston changes its location continuously inside the engine cylinder. Okay. So, this IMEP, so this indicated mean effective pressure. So, if I write here this indicated mean effective pressure is, so this is obtained from the indicator diagram with the help of indicator device, okay, or I should say write devices. So, this is very important to know that indicated mean effective pressure can be determined or calculated using indicator diagram with the help of indicator devices. So, IMEP is the indicated mean effective pressure. Now, let us discuss one method which is consistent with the measurement of indicated mean effective pressure using this indicator diagram. Okay. So, just for the sake of completeness I am writing here. So, this is indicated mean effective pressure. Okay. So, if we go to the next slide wherein we can see a schematic depiction or a schematic in this particular slide schematic is depicted just to make you understand about the device or mechanical system which is used to know or which is used to measure indicated mean effective pressure through indicator diagram. So, essentially this device is an indicator device. The working principle of this device relies on the accurate measurement of indicator diagram which in turn will be used to measure indicated mean effective pressure. So, what are the components? If we can see, though all components are not labeled in the schematic, you can see that this is essentially a spring. So, this is spring, this is a small drum, okay. This I will tell exactly the functionality of all these components or parts later on, but let us now first label all these components. So, this is known as stylus, this is mechanical linkage, and essentially this is engine cylinder, okay. So, let me write a few steps first, then that will help you to understand what are the steps used or to describe the functionality of this particular mechanical device or indicator device. Okay. As I said you that earlier, so essentially this device, as I told you earlier, indicated diagrams were produced by mechanical device or mechanical plotters linked to the engine cylinder. So, indicator device which will give us an information about indicator diagram, earlier indicator devices or earlier indicator diagrams were produced by mechanical plotters linked to the engine cylinder. So, essentially in this engine cylinder you can see on the top of the engine cylinder there is an arrangement, and that arrangement is again essentially a mechanical arrangement. So, let me write a few steps first. So, what you can see, this is the small cylinder, this cylinder A. So, if I again write here, this is a small cylinder. So, this A is a small cylinder, inside which there is a small piston. So, small cylinder with housing a small piston. If I erase this, and small piston inside the small cylinder will be having some to and fro motion against the spring, okay. That spring you can see. So, the piston is connected, the spring you can see, and so cylinder inside the small piston will have reciprocating motion and to and fro motion between, or I can't say between two locations. So, the piston will reciprocate inside the small cylinder, which is connected against this spring, connected to the spring against or some against the forces, okay. So, what I am writing first, you can see that small cylinder and piston, the piston is also small, these two are attached to the engine cylinder such that the pressures in the cylinder that will develop because of the combustion, force the small piston to move or to have to and fro movement against the force of a calibrated spring. So, this piston is spring loaded piston. So, this is the engine cylinder that I have already written. So, on the top of this engine cylinder, this mechanical housing is there, that is that housing is composed of one small cylinder, a small piston. The small piston, the arrangement is such that small piston can have to and fro movement between, inside the small piston, not between. The small piston can have to and fro movement inside the small cylinder, which is mainly due to the pressure that will develop inside the engine cylinder. So, when pressure develops inside the engine cylinder, that pressure will force the small piston to move off against the force of a calibrated spring, okay. So, then if we write number 2, so the movement of the small piston, the movement of the small piston is proportional to the pressure inside the engine cylinder. So, it is engine cylinder, okay. So, that means if the pressure inside the engine cylinder is low, movement will be low. If pressure is high, movement will be large movement will be there. So, that is what it is. Now, question is, second problem is, if you look at the schematic depiction carefully, you will find that this piston is somehow connected to a mechanical linkage that I have already marked or labeled in the schematic. So, if I go to write in the next slide that the movement of the piston is transmitted. So, number 3, the movement of this small piston is transmitted through a mechanical linkage. It is large mechanical linkage to a stylus, right. If we go back to the previous slide, let us describe it. So, the piston is getting or piston is having movement inside the small cylinder, but the piston movement is proportional to gas pressure that we have discussed. Now, the piston is connected to this mechanical linkage which is relatively large. So, that movement of the piston is transmitted to the stylus that you can see here through this mechanical linkage. Okay. And you can see in the right hand side of the schematic there is a small drum and a paper sheet is wrapped over the small drum. So, this small drum which is wrapped with a paper sheet outside. Okay. So, if we go to write in the next slide 4 that a paper sheet is wrapped around a small drum, okay, which is caused to oscillate, in accordance with the stroke of the piston of the engine. Strokes of the piston, this is not the small piston, strokes of the pistons of the engine, right. So, if we go back to previous slide again, so the small drum which is there, a sheet paper is wrapped around the small drum and the small drum is designed to oscillate in tune with the strokes of the engine. So, essentially that when it is intake stroke, compression stroke, power stroke and exhaust stroke, in tune with all these strokes the small drum will oscillate, that is how it is designed. Okay. Now, if we go to the next slide again, so what will happen it is the stylus that you can see which is connected to mechanical linkage or which is connected to small piston through this mechanical linkage, the stylus will be having or it will move up and down, and because the small piston will move up and down experiencing change in pressure in the engine cylinder, which in turn will allow the stylus to move up and down in that you can see, which is the stylus will move up and down which is parallel to the axis of the drum. Okay. But the drum itself is oscillating in tune with the engine stroke. So, if you go to the next slide, just if I write here that, so if we write here point number 5 that the stylus moves up and down, okay, parallel to the axis axis of the oscillating drum, parallel to the axis of the oscillating drum, and while the stylus is moving up and down which is parallel to the oscillating drum, in the course of this movement of the stylus it will produce a record of engine cylinder pressure. Against the engine piston position. Okay. So, the record if I write here the record thus produced is termed or is called as, is called an indicator diagram. So, essentially we wanted to have this indicator diagram, because knowing this indicator diagram we will now take an effort to have some quantification of the indicated work. So, from the indicated diagram, next task should be to have some information about the indicator or the area of that diagram. From there, from that area should be we shall try to quantify work done. So, area should be converted to work, and for that we need some constant. Okay. So, idea is that as the so try to understand drum, a small drum which is wrapped or with one sheet paper. Drum is designed to oscillate in tune with the engine strokes. So, certainly and drum will not be stationary, it will oscillate. On the other hand, that small piston will again move inside this small cylinder in tune with the pressure inside the cylinder, and since that movement is transmitted to this stylus through the mechanical linkage. So, we will be having one record of inside or cylinder pressure at different strokes, because small drum is also oscillating with the engine stroke. Okay. So, now we have this indicator diagram. Now, the question is, this indicator diagram is used to produce or used to measure indicated work by measuring area of that indicator diagram, but this method has some limitations. What are those limitations? This method is not suitable for small engine and high speed engine. So, if we need to quantify or need to measure work done by an engine, if the engine volume is very small and engine is having high speed. If the engine volume is small, you try to understand, if we try to go back to the previous slide, then you can see that on the head of the engine, that mechanical assembly is integrated. So, essentially the small piston, small cylinder, mechanical linkage, stylus, all these this particular mechanical assembly is placed on the head of the engine. Now, if the engine is very small, positioning of this mechanical assembly will alter or will affect the compression ratio, number 1. Number 2 is, certainly to obtain this indicator diagram that we have discussed so far is dependent on the efficacy of the mechanical linkage, because movement of small piston is transmitted to the stylus through this mechanical linkage. If the engine is having very high speed, mechanical linkage will be having some inertia, any mechanical device is having some inertia. So, to obtain information for an engine with operating at high speed, mechanical linkage may not be suitable, or even if we try to have some information using this mechanical linkage, performance or measurement will not be satisfactory. So, that way the limitation of this particular method that we have discussed is, or limitations are, it cannot be used for small engine and it also cannot be used for engines operating with high speed. So, let me write here for the sake of completeness. So, limitation of this method are as follows, right. So, this method cannot be used for small engine or an small engine Number 2, for high speed engines, this method is also not suitable. So, we have listed down. So, this method can be used for speeds up to 600 rpm. So, this is what it is. Now, let us discuss about. So, these are the limitations. Then what are the advantages of this particular method? You know that inside the cylinder, engine pressure is, or engine pressure changes continuously, right. And as I said you, measurement of instantaneous pressure inside the engine cylinder is not very easy task, though it is it may be possible using state of the art sophisticated instrument. Those are really possible with the advent of digital technologies. But still what will happen, that engine pressure will be changing continuously as the stroke length changes. Over and above, there are several unexpected situations, and those situations are if there is a delay in ignition time, if there is a delay in fuel injection time, also if there is a failure of failure of a nozzle to deliver atomized fuel or fuel with fine droplet. So, you know that, or even when there is a damage of the piston ring. So, all these expected scenarios may alter engine pressure. So, what I said, first of all, if there is a delay in ignition timing, if there is a delay in fuel injection timing, if there is a failure of the fuel injector to supply atomized fuel, and if the piston rings, if our piston ring is piston ring becomes non-functional. So, in all these scenarios, if we need to know about the engine condition or engine performance, this particular method is very suitable, because it will give some information at each and every stroke about the pressure that will be there inside the engine cylinder. Okay. So, that way it is suitable. Now, question is, let us discuss about the most important part is, we have discussed that fine indicator card is obtained with the mechanical, that indicator diagram is obtained using that particular device, that is indicator device. Now, what we need to get is indicator card. So, essentially using that indicator diagram we need to measure the area, and that area should be converted to work using some constant. Okay. So, let us discuss about indicator diagram that we have discussed in the previous slide. Indicator diagram can be obtained using the mechanical system or indicator device. Now, using this indicator diagram, what we need to know? We need to know the area or indicator area. Okay. So, area of the diagram. Indicator area. Okay. If we need to know area of the diagram, this is obtained using a mechanical planimeter that you have studied in your undergraduate course. So, mechanical planimeter is used to obtain this area. So, what does this device do? Mechanical planimeter is a device that computes area by tracing its periphery. So, if we know one diagram and if we use this mechanical device planimeter, that device can help us to compute area by tracing its periphery. So, let me write here just for the sake of completeness. So, you know this planimeter you know computes the area of the diagram by tracing periphery. But let me add here an important point. If we use this mechanical device to obtain or to compute area, someone needs to do it carefully, so that we know the diagram. So, we have to trace the diagram or trace the periphery quite accurately to obtain the area. So, someone who will be doing this task should be very careful, and the person should do practice quite frequently to obtain reliable and accurate results. Okay. So, now as I said you that once we got the area, then that area should be converted into work. Okay. So, this area should be converted into work and a calibration constant is needed. So, then area is converted to work using a calibration constant. So, essentially you know that if we write here, so if we write here this that I indicated mean effective pressure, right, that can be found more directly, right. So, we need to convert area into work, that is mechanical. So, if I write here that is work. So, if I write this IMP is essentially we know the area, right. So, area that is obtained by this mechanical planimeter. If I divide this area of the indicator diagram using the length of the indicator card, that is LD. So, this LD is the length of the card, right. This AP is the area of the indicator diagram. So, I should write AD now, because we have used suffix P in the context of piston area. So, in the context of writing or in the context of piston face area. So, we should now write AD. So, this AD is, so this is this is the indicator area of the indicator diagram, area of the indicator diagram. Okay. So, this indicated mean effective pressure is obtained by knowing the area. If we divide it with the length of the indicator card, that will give the ordinate length in millimeter. So, this is multiplied with constant k, that is calibration constant. So, this is calibration constant, right. So, thus we can write that indicated mean effective pressure, which is obtained using this indicator diagram, is AD by LD, where AD is the area of the indicator diagram that you have measured using the mechanical device, then using planimeter, and then finally, if we divide area using or by the length of the indicator card, then we will be getting unit or length in ordinate, So, basically you know that we will get ordinate in length, and if we multiply that with some constant calibration constant k, then we will be getting indicated mean effective pressure. So, this is you know that is what is used. So, you can see that particular you know is this particular method is helpful not only to measure indicated mean effective pressure, but as I said you, if there is any change in pressure inside the engine cylinder because of delay in ignition, delay in injection, fuel injection time, delay in you know or failure of valve or fuel injectors, fuel injector to supply atomized fuel, or if there is you know some issues or there is some issue with the fuel you know piston ring, in all these scenarios inside pressure will change and this method is suitable. So, with this let us now solve this numerical problem quickly. So, the problem statement is following data are obtained for the calculation of indicated horsepower from experiments on a single cylinder 4 stroke CI engine. So, if I write here, so it is given a single cylinder engine, but stroke is 4 stroke single cylinder engine CI engine, area of the indicated diagram that is 4.8 centimeter square. So, AD equal to 4.8 centimeter square and length of indicated diagram is 6.8. So, LD is 6.8 centimeter. Now, spring constant K is given 7.8 bar per centimeter, cylinder diameter is given D cylinder equal to 200 mm and stroke length that is LS equal to 550 millimeter and engine speed is 400 rpm. So, from this data set from this data we have to calculate the indicated horsepower using the method that we have discussed today. So, let me write the first you know that we have established today, that indicated mean effective pressure that can be obtained using the indicated area of the indicated diagram AD divided by length of the indicated diagram or length of the indicator card LD. So, this will give you know ordinate length multiplied with this constant will give the indicated mean effective pressure. So, let us first calculate this indicated mean effective pressure in the next slide. So, if we calculate indicated mean effective pressure for this particular problem, K is 7.8 bar per centimeter into area is 4.8 centimeter square divided by 6.8 centimeter. So, if we do this, then essentially what we will be getting is 5.51 bar, that equal to 0.551 megapascal. So, that is the indicated mean effective pressure. Now, from the diameter of the cylinder we can calculate area of the piston face. Essentially this is the pressure which is acting on the cylinder face, which will force the piston to move from the top dead center to the bottom dead center. Now, inner area of the cylinder is essentially you know the area of the piston face, though there is a clearance, but we can approximate that inner area of the cylinder cross sectional area is equal to the area of the piston face. So, that is AP equal to pi by 4 d cylinder square, and if we calculate the value, that equal to pi by 4 into 200 millimeter. So, 0.2 square. So, meter square, that is equal to 0.03 meter square. So, we can calculate average gas force on the piston face or on the piston, that equal to this indicated mean effective pressure 0.551 megapascal into area, that is 0.03 meter square. So, if we calculate it, it would be 0.02 megapascal, that is m Newton per meter square into meter square. So, that is mega Newton. So, this is the unit. Now, if we go to the next slide, then indicated, based on the data we have, we can calculate indicated work done per cycle. So, we have calculated so far the forcing due to pressure, that is indicated mean effective pressure acting on the piston cylinder. So, from the force we can now calculate the indicated work done per cycle is, so force that we have calculated is 0.02 mega Newton into, if we go back to the previous slide, you can see that stroke length is 550 millimeter. So, essentially piston has to move between these two centers, and that is the stroke length. So, if we go here, then that is 0.55 meter. So, it would be 0.01 mega Newton meter, that is mega joule, Newton per meter is joule. So, that is the unit. You have to write unit carefully, because otherwise it is, you will come up with a wrong answer. So, this is the indicated work done per cycle. Now, for a 4 stroke cycle engine, number of cycles per second. So, 4 stroke engine. So, you know that if you try to recall, perhaps you have studied this in your undergraduate course, that there are 2 revolution per cycle. So, if we calculate this, so that means RPM is 400 divided by 60, that is RPS, into there are 2 revolution. So, this is revolution per second by revolution, that is 1 upon second. So, that is 3.33. So, 1 upon second. Okay. So, already you have written per second. So, I am not going to write this per second, I am erasing this. So, finally, if we try to calculate indicated horsepower. So, indicated horsepower, that is IHP, that is 3.33, unit is 1 upon second, number of cycles per second into that indicated work done, that is 0.01 megajoule. So, if we calculate it, it is coming as 0.03 megawatt joule per second. So, essentially this is 30 kilowatt. So, this is the final answer to this problem. So, we have discussed this numerical problem essentially to illustrate the concept that we have learned today. So, to summarize our today's discussion, we can tell that we have discussed about a method which is used to measure the indicated work, and thereafter we have solved this numerical problem to illustrate the concept that we have discussed in today's class. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.